Welcome to the laboratory course. My name is Srinivas. I am one of the teaching assistant to Introduction to Photonics. Today I will be demonstrating one of the light phenomena, it is interference. So, using this Michelson interferometer. So as we discussed in class, the interference primarily has two things to do with. One is the constructive interference, another the destructive interference. You can observe that constructive interference and destructive interference in today's experiment. So, first we will build the Michelson interferometer and then use the Michelson interferometer to measure the wavelength of the source, the refractive index of a glass slide, the coherence length of the laser source, and then finally we see the qualitative understanding of the spatial coherence of the light source. So, this is the first component we use is the laser source. So, this is the red laser and this is the driver which drives the laser source. This is a beam splitter which divides the power into two directions with equal power, two mirrors which are mounted on the kinematic mounts, mirror 1 and mirror 2, okay. And we use a screen to capture the interference pattern. So, we will first construct the Michelson interferometer and then we will using this Michelson interferometer we will calculate the wavelength of the source we are using, and then we will find the refractive index of the glass slide. So, this is the glass slide which has a thickness of 1.1 millimeters. So, we will find the refractive index of this glass slide using the Michelson interferometer, and then we will do two more experiments which we will qualitatively understand the importance of temporal coherence and spatial coherence using the Michelson interferometer. So, this is the Michelson interferometer. So, we see here one laser source, a beam splitter and two mirrors and the screen. This screen is used to capture the interference pattern of the two beams. So, let us start from the source. So, light from the source is splitting into two directions. Let me call this as path 1 and path 2. Okay. So, the beam splitter splits the input beam into two paths, path 1 and path 2 with equal power. So, let us talk about one path by blocking the other path. So, I am blocking the path 2 here using a paper. Okay. Let us see what is happening in path 1. So, the beam which is reflected from the beam splitter will go straight and hits the mirror and goes back, okay, and again passes through the beam splitter, and it is you can see a spot on the screen here. So, this spot is because of the beam coming from the path 1. So, let us talk about path 2. To understand about the path 2, I am blocking the light in path 1 using the paper once again. So, we see here light from the laser source goes through the beam splitter and then strikes the mirror and goes back, again hits the beam splitter. Okay. From here the ray goes straight and hits the screen. So, here we can see the spot because of the path 2. Okay. Now, I will remove the paper here so that you can see two spots on the screen. One spot is because of path 1 and second spot is because of path 2. So, here the fringe pattern is not clearly visible in the camera. So, to see the clear fringe pattern, now what I do is that I will introduce a diverging lens just after the laser source, so that we can see a clear fringe pattern in the camera. So, you see the circular fringes formed on the screen here, where the center spot is bright and then you see circular fringes, dark fringe, bright fringe, dark fringe, bright fringe and so on. So, the circular fringes are formed because of the divergence lens which we used just before the laser source. So, the Michelson interferometer is set now. You can see very good fringes over the screen. So, using this Michelson interferometer, first we will measure the wavelength of the laser source which we are using. So, for that, so we already know that the wavelength of the laser source is given by the formula 2D by n, where d is the displacement of one of the mirror and n is the number of fringes or the number of fringe movement. So, this formula is already discussed in class. Now, we will measure the wavelength of the source using this Michelson interferometer. So, the wavelength is calculated by the formula 2D over n. So, where d is the path length difference between the two arms and n is the number of fringes. So, here I will first show how we vary the d value. So, as I mentioned before, this is the path 1 and this is path 2. So, by using this micrometer I can change the d value. So when I rotate this micrometer, you can see I can say that there is a change in the change in one of the path lengths. So we have a total of path length difference. So with that path length difference, we can see that the fringe pattern is varying there. To calculate the wavelength, so we need two parameters here. One is capital N value and the displacement d. So these two are related as we see here. So now what I do is that I will change the d value using the micrometer here and count the number of fringes. So now I will count the fringes starting from now. So now you see it's evolving 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14. So for that n value of 14, I will record this micrometer reading, which gives some d value. So using this d value, I will calculate the lambda by using that simple formula 2d by capital N. So now we see a clear fringe pattern on the screen. So in order to see this fringe pattern bit more clear, we will concentrate on the center part of the fringe. So in order to block the other part of the light, we will use an iris diaphragm. You can see this is the iris diaphragm. Here we can change the size of the opening here. So now we will pass the light through this tiny hole. So I am putting this iris diaphragm just after the laser source. So once I put this iris diaphragm just after the laser source, you can see that clearly that other part of the light is get blocked. You can see a clear fringe pattern at the center. So now we have completed measuring the wavelength of this red laser source. So now the next experiment we will be doing is measuring the refractive index of the glass slide. So this is the glass slide you see here, which I mentioned that it has a thickness of 1.1 millimeter. So I will place this glass slide in one of the paths. So here I am mounting the glass slide on one of the arm. So let's first understand what is happening when we place the glass slide here. So again, the beam coming from a laser source hits the beam splitter and goes to the glass plate, hits the mirror and goes back and strikes the screen over here. So now, so we are, as I said that we are planning to measure the refractive index of the glass slide. So you see that I can effectively change the optical path length by rotating the glass slide. So whenever I rotate the glass slide, the optical path length is going to change, because so the ray which is going in this path is going to see a more optical path length, just because it is more, the beam is going to the glass slide with more optical path length. Okay. So when I keep on increasing the glass slide, when I keep on increasing the angle of the glass slide, so the light encounters more and more optical path length difference, and because of that you see the change in the fringe pattern there on the screen. So this is the formula for the measuring the refractive index of the glass slide. So the parameters required for measuring the refractive index of the glass slide are the thickness of the glass slide and the fringe count and the wavelength of the laser source. So the wavelength of the laser source is already measured from the previous experiment. Now all that what we need to is to measure is the number of the fringe count and the angle which we rotate here. So you can here see the readings on this holder, glass slide holder, starts from 0 to 360 degrees in a clockwise fashion. So what I am doing is here is I am rotating the glass slide in the clockwise direction. So parallel you can see how the fringes are changing on the screen. You can count the number of fringes converging to a point in the center. So for this particular angle we see the count there. So based on the count and the theta and the thickness of the glass plate and the wavelength, you can calculate the refractive index of the glass slide. So we are done with two experiments. One is measuring the wavelength of the laser source, and then we have measured the refractive index of the glass slide. Now we will step into the third experiment, that is measuring the coherence length of the laser source, that is a red laser source. So as mentioned in the manual, the coherence length of this laser source is calculated by calculating the visibility of the fringe pattern. So, the visibility expression is given in the manual. So, what I do is here is I will change the path length difference between the two arms and see how the fringe is changing on the screen. So, each time for each movement I calculate the visibility based on the fringe pattern, and then when the visibility drops by 2, that gives the coherence length of the laser source. To measure the coherence length of the laser source, here we are going to use some additional components. So, I will list them here. One is the camera. So, in order to have a clear understanding on the fringe visibility, to see the maximum and minimum formation, so we will be using this camera. So, this camera is a silicon based camera. It can detect the this red laser source, red laser wavelength. Okay. So, usually this camera gets saturated for a few milliwatts. The laser source which we are operating here has a power of 5 milliwatts. So, the camera gets easily saturated. So, in order to kill the saturation effect, we use this neutral density filters. So, you see here these are the two neutral density filters. So, these are rotatable neutral density filters, which means that each angle will give a different attenuation value to the light. Okay. So, using these two neutral density filters, you can capture a light properly in the camera, and you can calculate the fringe visibility. So, here I am connecting the camera to the computer, and there is a software for this camera where you can see the images we captured using the camera. Okay. So, one more thing is this rail. So, as I mentioned before, so we have to change the path length difference, and we have to calculate the fringe visibility. So, the mirror is almost closely contacted to the rail. Now, I am moving the mirror along one direction. So, the advantage of this rail is that it will not give any tip and tilt, additional tip and tilt. There is only one movement, that is along the axis. Okay. So, now you see the experimental setup for measuring the coherence length of the laser source. So, as I mentioned that we are using some additional components for this experiment. So, one is a camera here. So, this camera is connected to a computer. You can see the computer over here. So, here we can see the interference pattern which is captured. Okay. So, as I mentioned before, usually this camera gets saturated for few milliwatts of power. So, I am using two neutral density filters. So, neutral density filters meaning that they will just attenuate the light. Okay. So, by varying this angle, so here you can see that I am using a screen just in front of the camera. So, this is to ensure that I can clearly see the fringe pattern on the screen, and then by rotating the neutral density filter, I can reduce the intensity on the screen. On the screen you can see that reduction in the intensity level. Okay. So, when I am sure that it has got to a minimal level of intensity, now I can remove the screen such that the light beam falls on the camera. Now, you can see the fringes are appearing on the camera. So, even here the camera is getting saturated. So, we need to increase the attenuation. So, I am rotating a bit more. I think I stop here. So, to start with we have to ensure that both the arms are of equal length. So, I am here using a scale to measure the path length. So, here it is approximately 15 centimeter from the beam splitter to the mirror, and similarly from on the path 2 you see that it is even approximately the 15 centimeters. So, now both the paths are of equal length, and we can see the interference, clean interference pattern on the screen. So, now what we do is that we will just keep on moving this mirror away from the beam splitter, and we capture the interference pattern on the camera, and by analyzing the image, you can actually calculate the line profile using the software. From this line profile, we can calculate the visibility using the formula I max minus I min by I max plus I minimum. As I mentioned before, we will start the experiment with the equal path lengths. So, here the path length 1 and path length 2 have the same value. So, that is approximately 15 centimeter. So, for that we see a clear intensity pattern on the screen over here. So now I am going to project this interference pattern on the CCD pixels. For that I am removing the screen over here. So now you can see clear interference pattern. These are the fringes. You can see here the bright spin, dark, bright fringes formed on the screen over here. So now what I do is here, this camera has an option to see the line profile of the interference fringes. So I can select the line which I want to see the intensity variation. So I am now selecting a line over here. So this is the corresponding line profile. You can see here the line profile. So to make it clear, I will zoom the line profile. Okay. So you can see according to this fringe pattern, you can see the line profile intensity variation. So you can take a value over here, some maximum intensity value. So the intensity values are here range from 0 to 255. So let's take I max of this value and I min some value over here, and based on this I max and I min we can calculate the visibility. So this is the visibility at path length difference of approximately 0 centimeters. Now what I do is that I will increase the path length difference by some 5 centimeter. So the d moment is 5 centimeter. So the total path length difference corresponds to 10 centimeter. Now you can see some fringes formed on the screen which are not pretty clear. So I will use the kinematic axis to arrange such a way that both the beams getting interfere again. So these are the interference fringes formed for the path length difference of 10 centimeter. So again based on the line profile, you can see the intensity variation over here. Again, so we can take one maximum value and one minimum value. Based on the maximum and minimum value, so we can calculate the visibility. So I will keep continuing moving this mirror away from the beam splitter. So by some 10 centimeter. Okay. So the total path length corresponds to 20 centimeter now. So for that again we need to slightly adjust the tip and tilt axis of the mirrors to see a clear fringe pattern. Okay, now you see a clear fringe pattern formed again here. So from this you can again calculate the visibility at this 20 centimeter path length difference. So again now I will move the mirror to some 20 centimeters away from the splitter, so that the total path length difference is 40 centimeter. So I will slightly again adjust the tip and tilt of the mirror. So even at the 40 centimeter you can see a clear fringe pattern forming. You can also see some additional fringes are formed apart from this these inclined fringes. There are also fringes in the other direction as well. So these fringes are formed because of the unwanted reflections happening at various optical elements in the setup. Okay. So in this way we can calculate the visibility at various locations. So as I discussed before, the coherence length is nothing but the location where the visibility drops by a factor of 2. So you see here the visibility is we see here the visibility is not getting reduced, it is maintaining throughout the movement. So for this laser source, the coherence length is way beyond 40 centimeters. We see that by moving the one of the mirror, we have changed the path length difference. So we have moved 40 centimeters, we have given a 40 centimeters path length difference, and we can see a clear fringes forming on the forming in the camera. So there is no drop in the visibility. So the coherence length of this laser source is far greater than 40 centimeter. So but the laser source which we are using in our setup is a semiconductor laser source. So usually the wavelength of this is 650 nanometer, and it has a line width of 1 nanometer. The line width is delta lambda. The delta lambda is 1 nanometer for this laser source. So for 1 nanometer line width, usually the coherence length is in the order of millimeters, but here we are surprisingly seeing the coherence length far greater than 40 centimeters. The reason for this unusual result will be discussed in the further classes. So now we have completed 3 experiments. One is measuring the wavelength of the source, the second one is measuring the refractive index of the glass slide, and third is understanding the coherence length of the laser source based on the visibility and the fringe pattern. Now we will move on to the fourth experiment, that is understanding the importance of spatial coherence using this interferometer, Michelson interferometer. So for this experiment I will be using a diffuser. A diffuser is a element which can scatter the light in all the directions. It means that the light coming from the laser source, it has one k vector. So if you pass this light through a diffuser like this, you can see here it is basically a scotch tape. What does it do is that when the light passes through this scotch tape, it will scatter the light, meaning that one k vector will be converted into multiple k vectors. So this will essentially reduce the spatial coherence of the source. So what we do here is we will put this diffuser just after the laser source or here, and we will see what is happening in the fringe pattern. So without the diffuser, we see a clear interference pattern formed on the screen. So the moment we put the diffuser, that is a scotch tape here, we see that the visibility has completely gone off, like so we don't see any fringe pattern formed on the screen. We conclude the Michelson experiment. So to conclude that, we have done 4 experiments using this Michelson interferometer. One is measuring the wavelength of the laser source here, and then we have measured the refractive index of the glass slide, and then we have seen the qualitative understanding of spatial coherence using this diffuser, and then we have tried to measure the coherence length of the laser source. So there are many applications of this Michelson interferometer apart from these 4 things which we did. So one is that this Michelson interferometer is also used to measure the gravitational waves. Also this Michelson interferometer is used in optical coherence tomography, so where we need a small coherence length laser sources. So one more application is that we can also measure the thickness of the materials. For example, we have measured the refractive index of the glass slide given the thickness. You can also measure the thickness of the glass slide given the refractive index of the glass slide. Thank you.